So tonight, Professor Imbens will take us through how randomized experiments have evolved, what they do well, and the practical challenges researchers face today. So please join me in welcoming Professor Guido Imbens.
Thanks very much for the introduction. So the microphone's working?
Yeah.
So it's a great pleasure being back here in Abu Dhabi. I've been a couple of times the last couple of years, and it's always been very pleasant. But this time of the year, it's particularly nice. So what I want to talk about today is randomized experiments. I want to talk a little bit about the history and kind of the background, and then give some examples of experiments that I think fairly recent experiments that I think are particularly interesting, and then talk a little bit about some of the work on experimental designs that is ongoing, kind of where traditionally randomized experiments were focused on relatively simple settings where we had a treatment group and a control group. Nowadays, much of the experimentation is done online, a lot of it by the tech companies, in much more interesting settings, in much more complex settings, leading to very interesting experimental designs. But yeah, there we go. Okay, so here's the outline. So let me kind of start by the fact that what randomized experiments, of course, are all about is trying to trying to understand causal effects. And there's the in introductory statistics courses, typically the first thing that is noted is that correlation is not the same as causation, and there's lots of examples there here on the left. One about there being a correlation between eating ice cream and getting sunburned, where of course there is no causation. And similarly on the right, one that is widely shown, showing a correlation between the number of Nobel Prizes per capita in different countries and the chocolate consumption. And much as I like chocolate, I think that there was not part of the path there. So how do we think about causal effects and causation as separate from correlation? And here, kind of, there's a long history in statistics as well as in econometrics, where from the beginning people were very much interested in causal effects. And so the way I want to think about it here in this discussion is very much in line with the way the early statisticians, Neyman in the 1920s, and later Rubin thought about it. I want to think about causal effect as a comparison of two outcomes for a particular unit in different states of the world, kind of where we want to think about a particular unit potentially being exposed to two different regimes, to an intervention. Maybe if I have a headache, I may take an aspirin or not take an aspirin. And what I'm interested in is the causal effect of the aspirin, is a comparison of what would happen to my headache if I took the aspirin relative to not taking the aspirin. Because the challenge is, and Paul Holland called this in a much quoted phrase, the fundamental problem of causal inference, you can't see both. I can't both take the aspirin and not take the aspirin and make the comparison. I have to do one or the other. And so I'm going to need to do it indirectly by comparing multiple units where some take the aspirin, some not, and then things get messier. And it's kind of the same way economists at the time that Neyman was doing this in agricultural settings were thinking about similar problems in market settings, where, for example, if you want to think about a demand function, you want to think about what the demand would be for a particular product at different prices, not just at the price we actually see. And we may, in the end, if we want to learn about the demand function, we need to kind of think about where the price is coming from. We want to think about the demand, what it would be for different potential for different prices you could imagine. And so in both these problems, the causal effect is a comparison of things we may see with things we don't see, we can't possibly see at the same time. And so to make that precise, it's often very helpful to actually think about the intervention that we're trying to measure the effect of. First time I taught a class on causal inference with Don Rubin back at Harvard in '96, we had a discussion about looking at the effect of child poverty. And so what people had done in that literature was essentially compare rich kids, outcomes for rich kids and poor kids, without really being very clear about what the intervention was. And so in this class, kind of we argued about the fact that really what you want to do is first start with an intervention. In this case, an intervention could be the government giving these families a guaranteed stream of income, a universal basic income type subsidy, and see what would happen then. Of course, doing that and actually doing an experiment would be incredibly difficult. So what we, out of the discussion in that class, came a study where we looked at people who'd won the lottery, where essentially they get a guaranteed income stream for 20 years. Typically, if you win the lottery, you don't get a lump sum, you get the check every year for 20 or 25 years. So it very much mimics a universal basic income. And so you can look at the effect of that on various outcomes, educational outcomes, labor market outcomes. But the key thing is you want to think about the intervention before looking at the outcomes. And then what really helps is if we can control that assignment mechanism. And of course, in economics, this is often very difficult. If we try to look at the effect of getting more or less education, it's very rare that we could do a randomized experiment where we can guarantee that the people getting more or less education are actually comparable. But in medical settings and in agricultural settings, often we've done experiments to make sure that if we see differences between a treatment group and a control group, we can attribute that with confidence to the intervention rather than to other factors, confounders that may be different between the two groups. Because this goes back to the work in the 1930s by Fisher and Neyman. By Fisher in particular, was very adamant that without randomized experiments, you could never possibly establish the causation. And as a byproduct of that belief, he refused to believe that smoking was actually bad for you, because he thought there could be other factors that we couldn't possibly control for. Now, the view that randomized experiments there are very special is very widespread. And of course, it's the basis of the Food and Drug Administration in the US and similar institutions in other countries insisting on randomized experiments in the drug approval process. But it's not universal. Here, there's a couple of quotes, including the first one by Angus Deaton, who won the Nobel Prize in Economics in 2014, I think, arguing that experiments have no special ability to produce more credible knowledge than other methods. So this is partly to make clear that the Nobel Prize doesn't give you any special authority in making these claims. My views are much more aligned with those of David Friedman in the middle, where he argues, and I think that's the prevailing consensus, that experiments offer more reliable evidence of causation than observational studies. In the end, the fact that we can control and do control and ensure that at least in expectation, treatment group and a control group are comparable gives us much more confidence, gives us the ability to quantify the uncertainty of our beliefs about the effect of interventions in a way that we can never really do in observational studies. Now, of course, when I teach this in my class, I also stress that some of this gets overemphasized. Fisher, in the original work on experimental design, stressed the importance, stressed the value of significance testing and the use of common standards. And he offered the suggestion that 1 in 20 was sufficiently small that we could dismiss chance as the reason for these differences. And now that has become a standard way beyond what is reasonable, where for drug trials, whether something is statistically significant has incredible importance in the drug approval process and greatly affects the value of companies, where that threshold is essentially completely arbitrary in the way it's used. And so here, these displays are from a case where a medical company did an experiment. They didn't find a significant result that would have greatly affected the value of that company. They decided to leave out the people from the experiment who had a severe case of the disease. It also left out the people who had very mild cases of the disease, only kept the people in the middle. And then lo and behold, it was statistically significant. And they touted that as evidence that it was actually working. Then later, they actually did a better, more high-powered trial. And it turned out that was all bogus. In the end, there really wasn't any effect there. But it shows how these methods can be abused or misused. Let me give some examples. And here, this is an interesting example in the current context of use of AI in the classroom. Here was an experiment which was done at West Point, where for a particular class that was run in a number of different sections. Students in some classes, in some sections, were allowed to bring technological devices, laptops, into the classroom, and other sections, students were not allowed to bring the laptops into their classroom. And then the question was how well they did on the common final exam in the class. And before actually getting to this quote, it turned out that having laptops in the classroom substantially, with a precisely estimated effect, lowered the performance on in the classroom. And this is why in my classes I now do not allow the students to bring the laptops. And there's other observational evidence that, again, kind of using AI for homework and stuff that doesn't lead to better understanding in the end, that there's clearly real value. And this is going back to the quote from the chair of the economics department at Harvard, David Leibson, who teaches a big undergraduate class, was also concerned that students bringing other devices to class don't actually engage with the material. One particularly interesting result in that paper is that there's actually a lot of evidence of heterogeneity of that effect. It turns out the effect is very much concentrated on the men. For the women, there's no evidence of any effect. And of course, there's a large psychological literature suggesting that women, particularly at that age, are better at multitasking and less distracted than men. In my class, I discussed whether it would make sense to have a policy allowing the women to bring laptops, but not the men. But I think the university administration would not be happy with that. Another interesting result was that the effect seemed to be bigger for students. We came in with better credentials, with higher grades prior to the class. There, I'm less sure what to make of this, because this is exactly where the power of randomized experiments is very clear. There's sort of a lot of reasons to expect that people could actually benefit from having electronic devices. It may make it easier to take notes. It may make it easier to do some of these other things. But there's other possibilities that people get distracted, do other things. And in the end, it's an empirical question. And we can compare classes that have one policy versus another, but these things are never conclusive. here, the experimental evidence is just very clear. In the end, it doesn't work. Having people have these devices distracts them, and it takes away from the understanding as clearly and precisely measured at the end of the semester. Here's another recent experiment that caught some attention, where kind of showing the value of AI. There's of course a lot of discussion in general now with AI having become very powerful, where it's actually helping, where it's actually improving productivity. And this is one of these settings where there's very clear evidence that it can make the workers more productive. This is in a call center setting where the employees are answering calls about a particular the piece of software. It's a complicated thing, so these are relatively skilled the people answering these calls. These calls take a fair amount of time, and having AI help there in answering these calls improves their productivity. It makes them answer the calls faster, get to the resolution faster, without any evidence that it lowers the satisfaction of the people who call with the problems. And again, there's lots of reasons, there's lots of arguments you could make why it may not help, or why it may help for some groups but not for others. But the experimental evidence here is very clear that overall it helps, and it turned out it particularly helped relatively inexperienced workers in this setting. Another interesting AI experiment was one where, in a management consulting setting, some teams of consultants were given assistance from AI tools or not. And here they were asked to do a number of different tasks. Some were relatively mundane tasks, sort of inside the frontier tasks, and it turned out there the AI was very helpful. It was very good at getting them to faster, more satisfactory solutions. But for doing tasks that were outside the frontier, that were on the cutting edge of things, there using AI tools actually made the product worse, made the results worse relative to the teams that were not using AI. Because here it very much feels like that's a point in time result where the AI may get better at what they can actually do. But again, it shows that you need to be very careful, that it's not the case that these things help uniformly. And the fact that you come up with examples where they help doesn't mean that that's going to be working in all different settings. Here's an example about where it was an experiment done at a Chinese travel agency where some of the workers were allowed to work from home. Working from home is, again, one of these questions where lots of companies have made different decisions. It's easy to come up with reasons why it may be bad in particular settings. You may lose out on interactions between individuals in the office, but it may cut down on commuting time. It may increase worker satisfaction considerably by making their day more flexible. For this particular company, where the workers were essentially working on their own on the computer, there was reason to believe that it might actually help. And it turned out, in this case, it helped in the sense that it didn't appear to affect. There was no evidence of any effect on productivity, but it reduced substantially attrition for the employees. It clearly raised employee satisfaction with the work environment and the way they were able to work, and cut down on in this case, often considerable commute times to the office. Now here, this is kind of a slightly more indirect experiment, but again, one where some of the results went against the conventional wisdom. This is a setting where there was a bunch of economists working at eBay. And so the eBay at that time was in the habit of advertising on Google on their name. So if you typed in eBay, you would get shown an advertisement from eBay. And there are lots of people clicking on that. And so from their internal metrics, it looked like that was a very good investment from their perspective. They paid a lot of money to have that advertisement up there, but there were lots and lots of people clicking on it. So it looked like a very sensible investment. But that was not quite answering the right question. The right question is really, what would have happened had they not advertised? And of course, people searching specifically on the keyword eBay probably actually mostly know where they want to go. And so even if the advertisement wasn't there, eBay, the organic search item for eBay would be very high on the page anyway. And quite plausibly, people would be clicking on the organic answer rather than on the advertisement if the advertisement was not there. And so to see whether that's the case, it doesn't make sense to just compare how many people click on the advertisement versus the organic answer, because the advertisement is higher up on the page, and so it's more likely to get clicked on. And so what eBay did was an experiment where in some regions they stopped advertising on eBay, on Google, and compared that to other regions where they continued advertising on eBay, on Google. And so what happened was very clear. If they stopped advertising, there would be no more traffic coming in from the advertisements, which is obvious because people couldn't click on the advertisement anymore, other than if people were traveling and stuff. But essentially, the traffic coming through advertisements for those regions would go to zero. But everything just went to the organic search answer. And so the overall traffic to eBay didn't actually change very much. And so despite the fact that based on the marketing team recommendations, they'd been advertising Google for years, it turned out it was very questionable whether that was actually a sensible investment from their perspective. Now, let me, I don't know exactly how much time okay, so let me make some comments kind of on modern experimentation. The traditional experimentation, especially the Fisher and Neyman framework, came from agricultural settings. I showed a picture kind of from the Rothamsted experimental station. And this was settings where they would look at the effect of using different types of fertilizer. And so they would be interested in how that affected the yield, say for corn. They would put fertilizer A on some fields, fertilizer B on other fields, grow the corn and wait till the end. The Fisher would smoke his pipe and then wait till the end of the season and measure how much corn was grown on some of the fields versus the other fields. Essentially the same setting still applies in medical experiments. We give different treatments to different patients and we see what happens to their outcomes. But now most of the experimentation, huge amount of experimentation, is done in online settings, where often where the context is a little different. Often we see the outcomes very quickly, whether people click on something or not. We also often have lots of treatments we want to evaluate. in a particular advertising campaign, we may have 10 different versions of an advertisement that we want to evaluate, or 10 different ways to influence people's behavior. And so one of the experimental designs that is actually, and a third difference with that setting is that in these settings with multiple treatments, we're not interested so much in estimating accurately the effect of each relative treatment. What we're interested in often is selecting the best one. And we don't really care how bad the bad ones are. We just want to know which one is actually the best, the optimal one from the perspective of a decision maker. And so in that case, it doesn't make sense to follow the traditional designs where you give equal amounts of traffic, equal amounts of experimental units to all the treatments, because very quickly you may already see that some of the treatments are not particularly effective. And so instead of continuing to send traffic, to send units to those treatments that are already known to be inferior, you're much better off sending more traffic to the treatments that are potentially the best ones. And so you can much more efficiently, much faster learn which treatment is the best. You can see that here in the exhibit on the right, where with these 3 treatments, instead of sending equal amounts of traffic to each of them, as in the left part of that, if you update along the way and lower the amount of traffic that goes to inferior treatments, you very quickly find out that the green one is the optimal one, and end up sending all the traffic to that. Actually, did that in one of my MBA classes at some point, where we had students design an experiment where they had people on Mechanical Turk do particular jobs, and at the end of that, they were the participants in that study were given a bonus, and the students were asked to design a solicitation for them to donate that bonus to a charity. And the question was, it was all the same charity. The question was, what was the most effective way of donating that charity? And so we first did it with equal amounts of workers to each of 7 groups. Actually, there were only 6 groups. One of them was a AI-generated solicitation, which actually did better than most of the Stanford MBA students here, as an aside. But so for the first 700 participants, we assigned them equally to each of the 7 solicitations, and we saw that some did much better than others. Then what we did for the second part in this multi-armed bandit approach, we send it to each of these arms proportional to the probability that arm was the best one, and that led us to de-emphasize some of these arms substantially, and led us to much more precise inferences about which arm was the best. It may be slightly too small to see this very clearly. We also had the class actually kind of rank the solicitations in advance of the experiment to see whether you would actually need to do an experiment, and turned out it was actually pretty hard for people to predict which of the solicitations would work well. Again, showing that doing the experiments is very helpful, that it really generates the information that is very powerful. Let me kind of wrap up kind of with one other class of experiments. So another challenge in many cases is inference between interference between units. So if for example Uber or Lyft wants to do an experiment involving their surge price policy or their tipping policy, they can't simply randomize the drivers to a treatment group and a control group. Because if they did that, and if the treated drivers were incentivized to actually show up more because they liked the new policy, that would affect the control drivers as well. The control drivers would be faced with additional competition from the increased hours worked by the treated drivers. And so they may actually the control drivers may show up less as a result of this increased competition. And so instead of randomizing individual drivers or individual riders, what organizations often do in those settings is randomize entire labor markets, entire cities to a treatment group and a control group. That doesn't give you enough power in these experiments. And so what they do to generate additional power is switch the treatment group and the control group back and forth in the way in the old agriculture experiments they would do with cattle feed, where they would try the same cattle, switching between different types of feed, not just randomizing the herds of cattle. And so that leads to much more precise experiments in many of these settings. And a sort of an extension of that is, and I'll make the next one the last slide, an extension of that is to kind of think of these settings as having two-sided markets. For example, in a Netflix settings where you could randomize both movies or the viewers in an experimental context, instead of just randomizing one of the groups, you could randomize both at the same time in a way of generating much more precise inferences than you would do in traditional settings. But let me stop here and make sure there's going to be time for Geoffrey here and some time for questions before turning it over to him.
Yeah, let's give a round of applause to Professor Guido Imbens. And we'll open the floor for questions. And may I remind the online audience to mute their mics and write your questions in the chat. We'll have a read through that. So please raise your hand, state your name and affiliation and your question.
So thank you, Professor, for the wonderful session. I'm Pankaj. I am from India. I head India's Quant Association. I have one question. We often talk about that correlation is not causation, but the point is that sometimes no correlation does mean there is no causation. And I think is there some incompleteness in data to determine causality or not? I would like to know your views on that.
Yeah, yes, correlation is not always causation. In fact, there need not be a correlation for that to be the causation. Kind of one traditional example is to look at the estimation of demand functions. So we may want to know what the effect would be of increasing prices on sales. And if you just look at the correlation between sales and prices, it could be positive, it could be negative, or it could be zero, because it all depends on how both supply and demand shift over time. So the presence or the absence of correlation is in general not informative about the presence or absence of causation.
Yeah. So do you see the limitations of data in determining the causality?
No, in the end, it's all about having the right type of data. In the demand and supply setting, we need to isolate factors that affect supply and demand to be able to get to disentangle the supply and demand in a market setting. And so in these more complex settings, and we'll be talking about it tomorrow, as well, in these complex settings, you need to have the right kind of data or have the right kind of experiments to disentangle the different forces and look at all the causal effects that play a role.
Thank you.
Thank you very much, Guido. My name is George Subelli from Khalifa University Mathematics Department. Following up a little bit on your answer about complex experiments and complex settings, do you see some evolution of causal inference with the advent of AI being more available? Is it possible to use AI to design experiments?
No, I think that's a very interesting set of questions. I think there's going to be a big role for AI in helping design experiments. I think I see the way the role experiments play is that they help us answer very specific questions. But a challenge often is to figure out which particular questions to ask. If you have a system where there's a lot of ways we can intervene in it, there's some things where we're very confident, we know what the effect of those interventions are, other things we're not so sure. And I think AI is going to be helpful in kind of integrating all that knowledge and telling us that this particular intervention will be particularly valuable in giving us answers that help us pin down the whole system, given the other things that we do know. So I think there's going to be a very useful role for artificial intelligence.
Okay, thank you.
Thank you, Dr. Imbens. My name is Saeed Al-Amri. I work at ADIA, and I'm a PhD student. I am actually researching causality, and your work is very, very big source for me, and I really, really enjoyed your work. I was actually, Dr. George is actually my professor at university as well. And I was talking to David earlier, and one thing we were talking about is dimensionality and causality and how that can be computationally expensive. How do you deal with a challenge like this? Because in my research, I found it very challenging. It takes a lot of time to compute and experiment on. Thank you very much.
Yeah, so again, that's a very interesting set of questions. So traditionally, in causality, we've studied kind of very narrow, very specific questions. We started with a particular intervention, and the question was really what is the effect of this particular intervention? But in bigger systems, the question is often much more, how do we intervene in this? We may have some goals, but how do we intervene in this system in a way that is effective, where there's a lot of heterogeneous the units or agents in this system, and we can intervene on different ways for different units. How do we do that effectively? And how do we design experiments that are going to tell us how to do these interventions efficiently? And that's where these dimensional questions come in. Because the machine learning literature has shown us that in many cases, we can actually reduce the dimension effectively, that even though in principle, there's a very big space to explore, looking at the right subspaces can be very effective. So again, I think they're using a lot of the modern computer science tools is going to be very helpful.
Take one more question.
Hello, my name is Ali. Thank you for the talk. It was very interesting. I work at ADIA, and I have two questions. I'm curious, do you let your students bring their laptops?
No.
Second question is, what are the limitations of modern experimentation, and where do you see it shine, in what field?
Yeah, so for the first question, in the end, when I was teaching this undergraduate class, we had a lot of discussion about whether the evidence from this particular experiment was actually useful for for informing the decision, I was co-teaching this class, and so we made the decision not to allow the students laptops. And when we discussed this, obviously the topic of the class was different. You could imagine that for some classes, it is very helpful to bring in laptops. If it's actually a coding class, it would be very helpful. The different students, so there's a lot of concerns about external validity, but in practice, that is the way things go. You have to make information based on limited data. And in this case, we felt that the data was close enough to the setting we were in, where we were making the decision, that it was helpful to base the decision on that. But that goes to the second question, the limitations of experimentation. We can never quite do the right experiment for a particular decision. We're always doing the experiment in the past to make a decision for the future. So we're always extrapolating to other settings, to other populations, to slightly different interventions. And so we need to balance the importance of making decisions now versus getting more information that is relevant for those particular decisions. But doing targeted experiments and learning the things we're most unsure about, that are most valuable for making good decisions, is going to mitigate these limitations.
Thank you.
All right. Thank you again, Professor Guido Imbens, for the compelling talk. I'm honored to introduce the next talk of tonight's evening. Professor Geoffrey West is the former president of Santa Fe Institute and a distinguished professor at the Institute as well. In today's talk of Professor West, he'll talk us through scaling laws from cities to companies, from organisms to other kind of scaling laws in terms of what changes when the size kind of changes. So the title of today's talk is Scaling Laws and Hidden Laws of Life, Growth, Death, and Innovation from Organisms and Companies to Cities and the Anthroposphere. So please join me in welcoming Professor Geoffrey West.
Right there. There you go. Can you hear me? Is it working? Yeah, good, good. Yeah, so this is a long, pretentious title, and it's all going to be done in half an hour somehow. So I'm going to talk, as was already mentioned, is in the title, everywhere from organisms all the way through to social organizations and even the entire planet. But I'm going to take a physics perspective, and I want to just spend 1 minute being slightly pedantic in just reminding you what that means. And I'm going to do it first by a quote from very well-known physicist Steven Weinberg, won Nobel Prize for unification of the weak electromagnetic interactions. He says, "Our job in physics is to see things simply, to understand a great many complicated phenomena in a unified way in terms of a few simple principles, to which I would add the search for underlying laws and principles leading to a quantitative, mathematizable, meaning computable, predictive, testable, conceptual framework." So that's it. So that's the sort of mindset I'm bringing to this. And that mindset, that whole set of principles led to this. All of this stuff around you is sort of stimulated by the investigations of the physical world. This, by the way, is my only attempt to use ChatGPT. But it also led to this, of course, something quite spiritual and deep, understanding the cosmos, remarkably. So much so that time goes this way, that we sort of understand to some extent in great detail, actually, the evolution of the universe from the Big Bang all the way through to the formation of galaxies and ultimately to the formation of planets and therefore of the Earth. And that's kind of amazing. And what we learned is that we live in this exponentially expanding universe, which everybody's sort of familiar with. But one of the most amazing things about all of that is that there's one place in the universe, which these laws have a very hard time trying to find out what's going on, because on there is all this mess, all this rubbish sits on this planet. All of this stuff, with all this wonderful stuff going on, and somehow that's unique. As far as we know, it's the only place in the universe that all of this stuff happens. And so it's kind of amazing that what's going on here is more complex, if you like, than the universe itself, because we can, and I will talk about that. So there's an interesting division between simplicity on the one hand, things that are sort of algorithmic, meaning we have formulas or a way of understanding. We know how to, everyone in this room in principle could build that airplane because there's an algorithm to tell you how to do it, as distinct from this, which we can't do. It's not algorithmic as far as we know, because this is a complex adaptive system. It's evolving in response to its environment, often over short periods of time. And complex adaptive systems have this property that they have multiple levels of organization, they contain huge numbers of agents, and they all have to act in some unified, coherent fashion for the system to operate, and that happens through networks. So you're all familiar with sort of classic networks, but also biological networks. And here's the amazing thing, and I'm not going to do this, I'm just going to tell you that the physics and mathematics of these networks leads to something that is extraordinarily simple, that is to these scaling laws. That is that here's scaling law for how metabolic rate, that is how much energy, how much food you need to have per day to stay alive, as a function of size. And it's plotted logarithmically, going up by factors of 10. And you can see something extraordinarily simple has emerged from this. This has been known a long time. This has been known for over almost 100 years. The most interesting thing about it is this predicts that this slope is 3/4. Therefore, it's less than linear, which means that you get more efficient the bigger you are. You need less energy per unit cell or per unit mass to stay alive. And I was told, I had no formulas in this talk when I first made it. Then I was told, actually, there's going to be some technical people here. And so last night I stuck in a few formulas before setting it up to show that I can still write them. And to approximate fractal, this fractal like self-similar behavior, that this thing sort of repeats itself. These networks have this extraordinary geometrical property. And what is sort of also interesting is that it's not just this, but it turns out that the structure of these networks leads to, despite the extraordinary diversity and complexity of life, to scaling laws. I'm not even going to tell you what they are, one after the other, with exactly the same kind of structure. Plot them logarithmically, they're straight lines, as simple as it possibly could be. Not only that, they all are predicted to have slopes that are simple multiples of 1/4. So number 4 plays this dominant role. And they're all things like, here's the amount of mitochondrial DNA, here's lifespan, here's, I don't know, height of trees, so on. All kinds of things across the whole spectrum. So there's this universality, this quarter power scaling, and it not only goes, as already mentioned in the introduction, obviously in the title of the talk, not just for biological systems, but in fact, across social systems, such as we're sitting in now. I found this quote. So there is this sort of wonderful unification that we see across things that superficially look different. And I'm going to expand on this for the rest of the talk. So this one I put in last night. So that namely, for those that read mathematics, if this goes like this 3/4 power, then per unit mass, therefore per cell, it decreases with size in a systematic way. Therefore, what I said a moment ago, the bigger the organism, the less energy is needed per cell. So your cells work less hard than a dog's, but your horse works even less hard. And so that's that systematic economy of scale, which means less damage is being done. Therefore, the bigger you are, the longer you live, because less damage is being done per unit time. And concomitantly, the less sleep you need, because sleep is a repair mechanism for the damage done to your brain. So here's data. This is this line. These are us, mammals, and you can see, I don't have a thing. You can see it's predicted to be, it was predicted to be this 1/4 power, and it is. And here's something amusing if you don't know it, that the theory, this theoretical framework predicts. There's lifespan, that's heart rate, which is predicted to decrease as 1/4. This increases as plus 1/4. You multiply them together, this cancels out. That's one. So heart rate times lifespan multiplied together predicts that the number of heartbeats in a lifetime is approximately invariant, because that's what. So the number of heartbeats of a shrew, which sits on the palm of your hand, which is about 1,000 times per minute, is much higher, much faster than a whale, which is beats about 20 times a minute. But if you add them up over the lifetime, it's roughly the same. There's the formulae, just to show that there's some stuff behind this. And there's I'm not going to explain it, obviously, but it's kind of cute that you can relate lifespan to how long you're going to sleep. So there's an intimate relationship, because they're both related to yourself damaging yourself through metabolism. So the thing that keeps you alive is slowly killing you. So I'm around here. Most of you are around here. So I want to move to this growth. So how does growth work? You eat, you metabolize, you send metabolic energy through networks, goes to the cells at the cellular level. It maintains what's there. It does repair, it replaces ones that have died, and then it adds new ones. So you put that into mathematics. And if you do that, it's simply a supply-demand question. The supply is increasing slower than linearly, but the demand is linear, because you want to keep adding cells. So eventually you stop growing, because supply cannot keep up with the demand, and you derive a curve like that. So that happens to be for a rat, but there's the prediction and there's the data. And so this sublinear growth, this 3/4, leads to this sigmoidal, so-called sigmoidal. You start quickly and then stop. And here it is. This is derivations for all the rest. And the theory is kind of cute, because it tells you that if you look through the right lens by rescaling these quantities appropriately, everybody follows the same curve. So if you look through the right way, and as I showed before, also if you look at the right way, everybody lives the same length of time. You saw the number of heartbeats was the same. So if you use the right metric, there's this extraordinary unification. Okay, so here's a summary. In the biological world, you're dominated by these non-linear scaling laws with this 1/4 power. There's an economy of scale. The bigger you are, the less you need per capita. The pace of life slows the bigger you are in a systematic way. Growth goes quickly and then stops, and then you die. And the thing can all be explained by the mathematics and physics of those networks. So now I want to move to us, so to speak, the Anthroposphere. That's really what the world looks like, as you know. And this is what goes on. And here's a picture made by a NASA satellite in 1820 at night. Of course, it wasn't NASA's mine. But that's what it would look like. Had there been a NASA satellite, that's what it would have looked like. Nothing. You wouldn't have seen anything, because there were no lights. And it's only, by the way, that was only 20, 30 years after the Industrial Revolution. Here's 20 years later, and you just see little, maybe if you're in the front row, you see a little bit. 100 years later, the year I was born, you start to really see stuff. And now, of course. So it's happening at a faster than exponential rate. We're adding over 1 million people a week, probably 2 million every week. And so everybody knew that we lived in an exponentially expanding universe. Most people don't realize as we sit here, we're sitting in a faster than exponential socioeconomic universe. That's why we're all going nuts and going crazy, and the world's beginning to fall apart. That's an editorial comment, by the way, not a scientific statement. So here it is. Here's our growth in terms of population. You're probably all familiar with it. We started out here as hunter-gatherers, learned language, learned sedentary behavior from agriculture, and then around here it all went bonkers because we discovered how to exploit fossil fuels and discovered entrepreneurship, capitalism, free markets, and it led to all this. Led to Abu Dhabi is a great example, and it went straight up. And every socioeconomic or Earth system metric, of course, follows, all this kind of hockey stick. Now, if you're a physicist and you see this, it looks like this, which is the specific heat versus temperature of propane gas. And in fact, this line is identical to the line of the growth of the human population on the planet. Except it's versus time, this is versus temperature. So let's increase temperature. Everybody knows, I think, what happens. And you know why, of course. It's gone from a liquid to a gas. And this is called a tipping point sometimes, which I hate, but it's a phase transition in physics. It's a singularity, because this is effectively going to infinity. And so the big question is that going to be like that? Is that going to happen? And if it's going to happen, is it next year, 10 years, 100 years, or 1,000 years? Or if maybe it'll never happen. Maybe we somehow miraculously keep going straight up. Okay, so I want to, how's my time? I will go fast. So that picture of the night lights was cities. And of course, those are just the night lights of cities. And of course, what it really is just fossil fuel burning on the surface of the planet, because that's what's driving it. And all of that is, so cities play a crucial role, and they're this marvelous machine. That's what is here. This whole Abu Dhabi is a machine that creates wealth, it creates knowledge, innovation, ideas. And the idea is, of course, the only reason for that is to bring people together in order to increase quality and standard of life. That's the whole point. Otherwise, it's completely pointless. And here it is. This is what happens. This is what cities are about. And similarly, unfortunately, there is the most fundamental law in science, the second law of thermodynamics, which says if you do something like that, you create entropy, junk. Have to, whether you like it or not. So inevitably, it may not be exactly this, but you create stuff like this. And so, and we need to learn how to mitigate that. And the only way of doing it is to understand what the laws are that are governing this. So that's the whole motivation for this. So the question is, I just showed you these emergent hidden laws of biology. Are there similar hidden laws of cities? Well, they are network systems. But they have something new in terms of networks. They have what we're doing here, social networks, interacting and exchanging information, again, to create ideas continuously. That's what this is. That's sort of a picture. Not a ChatGPT one, by the way. And indeed, that network, that idea of the infrastructural networks, the roads and electrical lines and so on, leads indeed to simple scaling laws, as in biology. So, and this is true of, this happens to be petrol stations versus population size, logarithmically plotted for 4 countries in Europe. But if you do it for countries in South America, North America, Asia, wherever, they all look the same. For any infrastructure, I just have petrol stations, anything. And the interesting thing about this is the slope of this line, it's just like biology, except it's 0.85, so 0.75. But more importantly, in social networks, the social interactions, they have this new phenomenon that in real time, we have this continuous positive feedback mechanism. I talk to her, maybe. She talks to him, he talks back to me, and we sort of build up on each other. We build ideas, and occasionally out of that comes an Amazon, or the general theory of relativity, or whatever. That's the whole point. And so what this leads to is, instead of sublinear scaling, the bigger you are, the less per capita, superlinear scaling, the more you have, the more interactions, the more ideas, the more wealth, and everything else. And I want to explain that. And instead of slowing the pace of life, you increase the pace of life. That's what the networks do, whether you like it or not. So here's the data. And they all have pretty much the slope of 1.15. This is property taxes in Sweden. This is restaurants in Netherlands. This is the GDP of France. This is crime in Japan. They all have the same slope, pretty much, 1.15. There's this extraordinary universe. Why? Because they're all derived from social interactions. And so here it is in English. If you double the size of a city within an urban system, then systematically you save about 15% on all its infrastructure. And at the same time, you increase all the good things, income, wealth, ideas, patents, and so on, but also all the bad things, crime and disease and so on, all pretty much to the same degree anywhere around the world. The data. And you can check it. Here's data. Here's what these are the ones I showed before. This is the connectivity between people measured. This is some enormous amount of data we did with some colleagues at MIT, measured using cell phone data to measure the connectivity between people as a function of size. And you can see by eye, it's the same pretty much as these. So I'm going to finish off. Can I take a few more minutes? Oh, 10 more, didn't I? Okay. Oh, well, okay. So the question is, can we extend it to the whole globe? Now, 20, 30 years ago, even, and certainly 50 or 100 years ago, it'd be nuts to think of the whole globe as a unified object, like a city. I mean, a city has, obviously, is inhomogeneous, and the way I've described it here, I'm averaging over the whole city. Can you average over the whole globe, and does it make any sense? Didn't make sense. Now maybe it does make sense. And we all interact with one another. Look at this place. I mean, my God, that's we've been here 36 hours, and everybody keeps telling us there's 575 different nationalities in this building. I mean, you know what I mean? It's this. So it's hugely globalized because of trade and so on, and but also of course, the internet mostly. So the question is, if it is, then when you measure these socioeconomic and Earth system metrics, they would then look like they do in cities. In other words, they would be very simple scaling laws. Otherwise, they'd be all over the map if there weren't some unification to it. And here's the data. This is energy, GDP, and water use. You can see there's kinks in it and so on and so forth. But you can see there's evidence of simple scaling. And I've got the exponents up there. They're all superlinear, as you would expect them to be, given what I said. And so this is sort of evidence that the world really is globalized. And now I'm going to very quickly go through this, the same thing I did when I did for organisms. We're going to talk about the time evolution, the growth. So here we have to introduce something called social metabolic rate, which I will talk about in a minute, that gets allocated again between maintenance, keeping everything the way it is, and then adding new stuff. New people, new buildings, new ideas, whatever, okay? So social metabolic rate. So that was the metabolic rate I had earlier, and that's basal. I didn't stress this. That's the metabolic rate that you're operating at now. And what I didn't emphasize is less than 100 watts. So each person in this room is operating less than an old incandescent light bulb. That's your 2,000 food calories a day. Now, I didn't realize I had this up here. There we go. There you are. Now, you have to run around and hunt and gather, and that increases it by a factor of 2 or 3. And I didn't put the data in. There it is there. Now you can ask, what is that's your biological active metabolic rate. And for hunter-gatherers, we fit very well on this. But we're no longer hunter-gatherers. We now have all this stuff around us. Each one of us, you can ask, how much does it cost, so to speak, in energy to keep each one of us alive in the standard to which we've grown accustomed to have a car and buildings out there and roads and being able to fly back to the United States and all the rest of that stuff. There it is. It's way up there. It's about 11,000. I think I have a graph. Yeah, it's about 11,000 watts. So that's equivalent to a 30,000 kilogram gorilla. So you can turn it around. How big an animal is each person in this room, roughly speaking? You weigh the equivalent of 30,000 in terms of the energy that you're using. Therefore, it's not 8 billion people roughly on this planet. It's actually close to 1 trillion in terms of the actual energy use they use as a biological organism. Okay, I missed this out. So, unlike in the biosphere, where the supply cannot keep up with the demand, here we have the opposite. We have this superlinear behavior. So supply is continually increasing on itself as it gets bigger. And so it completely outruns the demand. And so you get open-ended growth. I'm not going to write down, I didn't write down any of the equations. And so you get this, I'm just the cartoon version, that for any socioeconomic metric, you have this, which is what we see, which is the graphs I showed earlier. And that's great. So this is good. So this is great. We have this idea that we have these social networks. We have this feedback mechanism, positive feedback. That leads to superlinear scaling. Superlinear scaling leads to this super exponential growth, which is what we see. So that's all very consistent and nice. And you can, it fits very well with data for individual cities, and it fits beautifully for this kind of growth and the growth of all these. I'm not going to show you that. You just have to take my word. But it has a fatal consequence, a potentially fatal consequence, and that's given by this dotted line, and that's called in mathematics a finite time singularity, because what it says is that if you continue on this, you go to infinity, which is nuts. You can't have an infinite GDP or whatever. So, and the theory tells you what happens. This is what we had for propane. You remember, it crashed. We're fortunate, it doesn't crash. It goes slowly. It sort of stagnates and then goes down. It depopulates. This system starts to depopulate once you start to cross this singularity. And so the question is, how do you avoid that? The way we have avoided it is the following, here's again, just a cartoon version. Here's this graph, this growth, but this is within a given paradigm. This could be, I don't know, the Bronze Age, could be the beginning of the Industrial Revolution. It could be we've just invented computers. Could we invented the internet? But there's some major paradigm which sort of dominates the way life is, so to speak. And so the idea is to avoid it, to avoid collapse, you need to make a major paradigm shift, a major innovation, reinvent yourself so you can start over again, and avoid the possibility of contracting. However, you're going to hit another singularity. So it's obvious what happens. you have to keep doing it. So if you want unbounded growth, you require cycles of innovation. Well, people have said that for probably 1,000 years, for all I know. However, this tells you that yes, but you have to do it faster and faster. Something that might have taken 100 years, 1,000 years ago, now only takes 10 years. And it tells you, this is a theory, so it tells you what the time is between these. And here's some data. I have no idea who this person is. I found this on the web. I just stole it because it looked like mine. And these numbers are how long it took for one of these, I'll say, inventions. So this is sort of a slightly different, but to reach 10 million customers. So it's a proxy for the acceleration of time, or acceleration of pace of life. And these numbers fit perfectly that. And I'm going to miss this graph out about singular because I'm getting late. And I'm going to finish off with two things, if you don't mind. I'll do just a few minutes. I have 2 more minutes going to this. So if you take the theory that I just described in words, it has a following prediction, which is written there, and I'm going to write the mathematics on the next slide. But what it says, if you plot one of these socioeconomic metric about how far you are from the singularity, logarithmically, amazingly, that should just be a straight line for the globe. There's the mathematics. You have a form. This is the formula as you approach the singularity, and the theory predicts what this is the value, the time of the singularity, and this is an exponent. Both are calculable from the theory, and what it says is what I said down there. That's now in mathematics, and here's the data somewhere here. There it is, data. This is for water, and that's for energy. And what you see is kind of interesting. You do see a straight line. We see two straight lines. This is just data, so you don't have to believe any of the theory I just told you. This is just the data of the globe. And you can see there are two straight lines, which says, and you ask, where does it cross? It crosses somewhere in the mid-70s. So we somehow avoided some potential singularity in the mid-70s, which leads to speculate, what might that have been? I don't know. The oil crisis, the beginning of globalization, the rise of the women's movement, all of these were, anyway, it's kind of, I leave that hanging. Just to summarize this, unbounded growth leads to this finite time singularity and potential collapse, meaning depopulation. And by the way, I remind you, as we speak, there are many parts of the world depopulating, countries in Europe that are depopulating as we speak. And you can only do it by making some major innovation, major transition. I had this quote. I don't know why I put it in the end, but anyway, we live in a society exquisitely dependent on science and technology in which hardly anyone knows anything about science and technology. And I think that's a serious, that's Carl Sagan, I don't know, 50 years ago, maybe. And I think that's a serious problem. And it's a particularly serious problem because as far as I can tell, there isn't a single global leader, except maybe in China, that isn't part of that. So that's part of the issue, is that we have complete disconnect. And I assume everybody knows who von Neumann is. You wouldn't be here without him, probably, or at least Abu Dhabi probably wouldn't be. But the whole architecture of computation, even artificial intelligence, well, economics, game theory, did everything. Great applied mathematician. Anyway, he made this statement in 1953, the ever-accelerating progress of technology gives the appearance of approaching some essential singularity in the history of the race beyond which human affairs as we know them could not continue. So that was a very remarkable comment. The weird thing about von Neumann is that everything he did, he mathematized. That was his great contribution, except this. It's sort of weird. I don't know why he came up with this. So in some extraordinarily modest way, I feel I've scratched the surface of trying to put some things on this. Now, and I'll finish with this, the last part here. This is all an example of this accelerating pace of life, which is causing tremendous problems for all of us, I think. And part of the problem is this, that we need to adapt faster and faster. But we have the same brain and the same biology, and that's a huge issue for all of us, I would say. I'm just going to throw this on, because something we just started is, and I'm not going to go into it, other than governance in such a world, because, and I've done it with a young man named Adam Day at the United Nations, it's just this statement that the world has been accelerating, the pace of life accelerates, yet all our institutions, and especially our governance, at best goes linearly. And we're getting a mismatch. We're still governing things the way we did almost certainly in the 19th century. And so that's a question. So this is some work that we've started to do on trying to develop ideas to how you might adapt some of the stuff I've presented into governance issues. And as we said, we have Holocene institutions for an Anthroposphere era. So I think I'll finish there, and I'm sorry. No, I do want to show one thing. I don't want to show, this is all rubbish. This, because these are the people who did all the work. And these people who did all the work, and they're quite an eclectic group. We have two of our postdocs. She's at MIT. She's at Sloan School of Management Business School. She was at she's a Kellogg professor at Kellogg. So it's very eclectic, even though they came out of physics. And part of this work, and it's part of the essence of what our institute is about, is bringing people from multiple disciplines together, because you can't do this work on your own, and you can't do this group if you're all physicists or all economists or anthropologists. You have to bring everybody together, and that's really the main lesson to take home from this. So I'm sorry I went on a bit too long. Apologies. Sure.
Thank you, Professor West, for that compelling talk. I think we'll open the floor for questions for 10 minutes.
So first of all, thanks a lot. My name is Babis Hatzikiru, and I'm working in Khalifa University. I'm working on mathematics of life. So I'm using mathematics to describe biomedical phenomena. And actually, it's very nice to see you here, because you were one of my PhD heroes when I was doing my PhD in Dresden. And I see here Dirk Helping, where he was in Dresden by that time. So I know him from that time. So my question is following. When your work, you are implying actually a kind of conservation law.
Yes.
Where you have, here heartbeats and...
it's basically, I mean, in simple terms, it's just conservation of energy and resources.
However, biological systems are open systems. So how this conservation law takes place? And one comment, and I finish. There is one biological system that works super linearly, and this is tumors.
And it's what?
Tumors. Cancer.
No, it doesn't. It's not quite true. It's not super linear.
Actually, there are the last Nature Physics paper.
We could. It's.
But anyhow, we can discuss.
Yeah, we'll talk about that, because we've done quite a bit of work a long time ago, well, 10 years ago, on applying this to tumors, and it's not super linear, but it's it's not like you and me either. So it's anyway. We can talk about that separately.
Regarding the conservation law, since biological systems are an open system, how do you think it takes place?
Oh, no, the conservation law is within the body, of course, because you remember, it's that the conservation law is you take in, you metabolize, so you have this metabolic energy, and that's what it is. What does it do? It basically does only two things. You can at least allocate it that way. As I say, between maintaining what's there and then growing new stuff. And in the state that all of us in this room are in, we don't grow new stuff. All it does is keep you alive, fighting the entropic forces of all the damage that's being done. So, you know, what you're talking about is if I then include the externality explicitly in it. So I've already, I mean, the whole definition of metabolic rate is in terms of the energy that turns out to be useful. I mean, that is, it's the free energy that's available. So,
Thank you.
So thank you, Professor, for the wonderful talk. These days, there have been discussions that on one hand, there is physics, on one hand, there is a human behavior, complex human behavior. Both have their own complexities, lot of similarities as you talked about. But do you see some fundamental difference between the human behavioral system and the physics system? Because at times when in financial markets, we tend to study those human system. So I agree that a lot of this statistical physics, singularity, critical state, all those things resemble. But do you think there is a fundamental difference between two systems in the degree of complexity?
I'm sorry, what's the question? What is?
Do you see the fundamental difference between a degree of complexity in a physical system and a complex human behavioral system?
Well, they're different. I mean, you know, they're both, you know, the biological system. I mean, both are complex adaptive systems in the sense I discussed at the very beginning. They have enormous numbers of agents. They have multiple levels of behavior. There are these emergent laws that come out of it. And part of it, which I didn't emphasize, which is a major hypothesis or assumption in the theory, that is, those laws arise from the tendency towards optimization that comes about from the continuous feedback mechanism from you know, survival of the fittest, competition, and so on, whether it's in a social setting or in a biological setting. And that's a big assumption, but that's what allows one actually to derive all these various equations, which I didn't show you, of course. But and in fact, it's kind of amazing that what it says is in this very coarse-grained way, all these systems are tending towards optimizing. One of the questions is, what is being optimized? I mean, you know, obviously a city is not optimizing in the same way that you are, in terms of your circulatory system, for example. So, but the commonality is this idea of optimization, and that optimization is manifested only after a very long period of time.
Thank you.
Hello.
Yes, so it's me. Yes, thanks, Professor, for interesting talk. I'm Kwon Nguyen from ETNOC. I would like to link your talk to the previous talk with causation and correlations. And I wonder if there's some causal explanation of the mechanism when you apply that in the social phenomena, or there's like control experiments in a social setting to verify the equations or the theory. Yeah.
Well, I think, no, it's interesting because I was thinking that in your talk, because I could have, one way of presenting this is to first show the data, just as you did. And there's a nice curve, there's lots of data points, there's not, and the question is that causal, or is it some, you know, just, there's many things in between, so to speak. And so that's why you have to have a theory. I think, I mean, that's the physicist viewpoint. Anyway, you know, in order to make sense of that, you have to have a theory. Otherwise, it's a phenomenological relationship, for sure. But whether you could raise it to the sense of, quote, a law, whatever that means, but then relies on theory, meaning that you have a mechanistic explanation for why it's the way it is, and that's why I actually had those first couple of slides about physics, that it should also be quantitative and predictive, so that you can then make predictions about things maybe that haven't yet been measured, which I didn't show you on this, but there are plenty of those. So it's very much, I mean, it's a very conservative, classic scientific methodology. And the problem only occurs, I mean, in physics, I don't think there was ever a problem, because physics always went hand in glove with theory. In the social sciences, because it's very hard to do experiments, it's very hard to develop any significant theory, we had exactly this problem that Guido had to address. I mean, that's the problem, is that you have these phenomenological relationships, and the question is, are they representing something causal and mechanistic, or is it that, you know, as you say, on a hot day, eating ice cream and swimming, or whatever it was she was doing, are, you know, just two things that came from something else. And biology, some of the biology behind this is actually replete with things like that, by the way.
Hello, can I ask a question, please? Hello?
Oops.
Hello?
Go ahead, Alex.
Oh yeah, this is Alex. I work for ADIA. Very interesting presentation. So two questions. You know, in a sense, like we all know Hooke's law, which connects to, you know, like force and displacement and all that as a linear, and then we can write a quadratic or power ordinary differential equation and obtain the singularity exactly like you have described. But we all know that dependence, like the reason why there is a singularity is because the wings are assumed to be x squared or higher order throughout the whole displacement, which is obviously not true in general. So is it not a much simpler explanation is that you know, the kind of, say, ODEs or PDEs or even functional differential equations which you use are simply not behaving at x squared or above when you deviate from the equilibrium very far? That's my first question. And the related second question is that you were talking about progress, like unlimited in many respects, but there are various things like diseases and wars and all other nasty things which can restrict this progress quite dramatically. So what is your overall view of this possibilities and eventualities?
Well, your first, I don't know how to say this, your first question is not relevant to this. I mean, first of all, Hooke's law and x squared play no role in what I did, that's for sure.
I respectfully disagree. Because if I were to write down this equation as dx by dt is equal to a x squared, I would get the same singularity as you did, and nobody knows.
No, you wouldn't. You actually wouldn't.
I would absolutely.
Okay. Okay.
I mean, look, you know, you can check.
You would. I wouldn't. So the great thing about science, by the way, of course, is that this is that we can settle this.
Yes, absolutely. So unfortunately, I will not be able to see you today, but hopefully some other time we can settle it. But we can very easily verify.
What was the second? What was your second question? Oh,
well,
wars.
My second question is, you were not talking about wars and other things like that.
No, I have not much to say about wars, because that's, you know, so this. Wars are in the category of other things that have been obviously completely ignored in this, like metrics like happiness. So, you know, it'd be nice to know how happiness changes with size and so on and so forth. There are crude attempts at measuring it, but wars, I mean, there is crime comes in this. We can do crime because crime is a constant background phenomenon of social life. wars sadly are a constant background for the planet, but they're very singular in their location. It's not like, I mean, crime occurs sort of, roughly speaking, everywhere. So I don't know, I don't think, I can't say anything about wars. Yeah, please, I'm not
Okay,
sure.
thank you. I don't have any further questions. I appreciate it.
So I think what Alex was asking is, prior to reaching the critical point, new mechanisms would come into existence.
Oh, I see. Yes, no, that I completely agree with. Absolutely. I'm sorry. Thank you. No, in fact, you know, I didn't have time, of course, to go into speculations as to what happens as you approach this. But you're absolutely right. I mean, what I believe, my speculation is, you know, you never actually get to that point because there will be social unrest. And there will be starting, you know, the crumbling of the social fabric, so to speak. And that's what we want to avoid. But that's my guess is what happens. And so I agree with you. Wars and conflict and general unrest would be the phenomenon because people are, so for example, the other thing is, it's not what this suggests, it's not a no growth situation we move into, but if we just continue and nothing changes, that is, we don't do anything, and AI is not, which it might be, a paradigm shift, might be, might not be, or electric cars might be, for all we know, who the hell knows. If there's nothing like that that causes a new paradigm to take over, then we have a decrease, we have degrowth. And no, I don't think anybody has really much thought about how to deal with degrowth. If you start having empty buildings or you don't have people around to do whatever the work is needed and so forth. And that's a whole different issue. But before then, almost certainly, because those will be disruptive forces, it will lead to social, I think, given the history of the planet so far, it will lead to conflict and wars. And it may even be that some of the wars that go on today already are manifestations of that. Who the hell knows? If I were maybe a historian, economist, maybe I could, that would be an interesting project to see to what extent these wars have their origins in some dynamic like this. Anyway.
Sorry.
Oh.
Simon Grange, tied up with the University of Birmingham. I appreciate what you're saying and trying to put a historical perspective. Over the last 500 years, we've really seen the evolution of society over a city-state sort of principle. The fascinating thing is, if we go back a couple of hundred years, Bazalgette was the savior of London because he put a sewage system in when it was reaching about 2 million people. Otherwise, it would have failed to grow.
Right.
Vancouver has also started to become rather limited at about 2 million. And there seems to be this sort of this watershed, or at least a gate that has to go through for city, even though you're showing this. Yeah. And so my real question is, as the time frame between these quantum leaps is decreasing, are we also seeing the ability to get to bigger size cities before they start to reach that threshold, bearing in mind that Abu Dhabi's, I think, 1.5 million at the moment?
I don't know the answer to that question. It's a very good question. Thought about it a bit, because this, so this is an ideal, obviously, this is a toy model idealized theory, which I believe captures many of the essential features, but many other things are left out, obviously. And so, just taken at face value, the city would just keep on growing, unlike an organism, most organisms. But of course, something else starts to happen as a city grows, and it already has happened in many cities that you're familiar with, and that is that first you have to back off and ask yourself to define a city. What is a city? So you may think it's just all the buildings. That's sort of an obvious thing. But no, I don't think so, because the most important thing about a city are the people and its interactions. I said the city, the whole point of a city is to get people to interact and to foment ideas, innovation, wealth, increased quality of life, et cetera, et cetera. So a city should be defined primarily in terms of its social networks. So if you're not connected to the city in some way, and you could define that as saying, if you don't come into the city, say, at least once every 3 months, if you don't connect with someone else in the city, the network of the city, you're not a citizen. Which is sort of weird in a way, because if you commute, I'll take America, if you commute from Boston to New York every week and work there, you're a citizen of two cities, which is fine. But you're part of that network, so you have to define the network. So what happens now, going back to this open-ended growth, what begins to happen is that network starts to balkanize, bifurcate. So you get, even though it is physically contiguous, a city is no longer socially contiguous. It breaks into pieces, and you know many instances of that. The other phenomenon that takes place is something like, think of Los Angeles. It's a city, its metropolitan area is close to 10 million people. And as you well know, it operates on the automobile, and it has, you know, the 12-lane freeways. Now, if you keep expanding it, now let's think, suppose you want to make Los Angeles the size of Tokyo, 30 million people. Well, and you still have the same transportation, you're going to have 24 or 36-lane highways and 10-track railroads and so on. Well, in principle, you could do that, but in practice, you're never going to do it. And that's what leads, those kinds of phenomena, which are not built into any of this, of course, start to limit the growth of what you would call the city, and it breaks up. So Los Angeles can sprawl out, but it's not one city any longer, and it isn't. So that's a partial answer, anyway, to your question. In other words, again, just to take it as a academic challenge, it would be extremely difficult to predict the asymptotic size of a city in any given instance, unless that is something that probably depends much more on its history, geography, and culture. And I should have said this maybe, but all these laws, one of the remarkable things about them is they don't depend upon history, geography, and culture. They seem to operate across the globe. And that's, by the way, just one last comment, that's because people are pretty much the same across the globe. and the cities are just representative of us. That's why the laws are the same everywhere. We're all pretty much the same in terms of, in this coarse-grained way, in terms of social networks, social interactions.
Host Simon with ADIA Lab, and I have the privilege of asking the last question, but I first want to thank Guido and Geoffrey for truly outstanding talks and coming here to Abu Dhabi to present them to us and engage us in conversation. Now, my question is about scaling laws, and there were about 2 years ago quite an intense set of publications coming out of OpenAI and others that claimed AI improves on scaling laws. And if I give your interpretation on what the AI believers formulated was that they're heading towards a singularity, which is the arrival of AGI. And I did never believe this. And I was wondering if you looked at this and if you want to comment on the AI scaling laws. And
my God. Well, I did see those because they were sent to me. Someone, and I looked at them and I thought, first of all, I thought the data was so limited and so sparse, really, that I didn't feel you could make any serious conclusion about it. I think you need much more. And then, to be honest, I'm embarrassed to say I lost interest. So I have nothing more to say other than I have a very conservative view of AI, you know, which is mostly just anecdotal, but so I can't really answer your question. I'm sorry.
If you don't mind, thank you very much. It's all fascinating, but it's also unsettling because it's so deterministic.
Yes.
And it's universal, and the determinism is universal. There's no room for randomness. There's no room for free will.
No, but that's I should.
Can you say something about whether we can break out of this scaling as a humans?
No, there are two things here. There are two things here because I didn't have time in this. I have slides which addresses, first of all, this question of variance and random. And that's one of the big questions. How much variance, how these are statistical laws and they're coarse-grained and what they say, put it slightly differently. Let's go to biology, which is, we don't have the same emotional reaction. So in biology, what it says is that despite appearances, a giraffe is a scaled-down whale, right? And we are a scaled-down giraffe. I mean, in terms of all the life history and physiological measurements you make, obviously, if you thought necks, the length of the neck, were a absolutely crucial fundamental element of all mammals, we'd be huge outliers. I mean, the giraffe. I mean, anyway, you know what I'm saying. Yes. So, so one of the questions is, how much can you violate these? So they're not laws. They can't be thought of as laws as in physics. There are these statistical laws. On the other hand, they do come from underlying principles and underlying mechanisms, but those mechanisms are dominated by just one or two variables, which is sort of amazing, actually, that you can get so much from that. It tells you what are the dominant variables that are determining the organization and time evolution of these systems. Now, I think you were also asking about the depressant, the idea that everything's getting faster and it's all going to fall apart, is what you're asking. No, so one of the things that I think is important also to recognize is that these when we think of a paradigm shift or major innovation, suddenly now in this period of time, certainly the last 20, 30 years, we just take it for granted. That means technological, right? We mean, that's why I said, it could be AI, the next one, or electric cars or whatever. But of course, innovation, could be a social innovation. That is, it could be that, we somehow don't buy into what this is doing. That would be a huge, how should I say, social change. That has happened in the history of mankind, right? I mean, that's why there are people like Jesus and Muhammad and Martin Luther King, and I hate to say it, Donald Trump, who have made enormous changes to things that we would never believe you could change. So, so one possibility is that, we have some charismatic person that gets us all to recognize what the problems are and to, change the whole mode of social interaction, which is hard to believe, but, that's another possibility. It's another speculation. You're in? Okay. So, that's so I don't know whether that's even a possibility or whatever, but it is, but, I need to, that's partially why I put in that slide of Carl Sagan, because one of the most disturbing things is what he says. We live in this society that's completely dominated by science and technology in terms of the way it works, and almost no one knows anything, how it works. And especially the people that are leading us. And so that I consider a serious problem, and I don't know how to address that. Thank you. Anyway, so.
Thank you so much, Professor West. Thank our speakers again for joining us today, and thank you all for joining us. We invite you to carry the discussion over dinner and networking. Also, please, if you'd like to learn about the ADIA Lab activities, you can watch out for the emails that we send. And in the website, we have kind of a brief description about the activities and the events that we hold. So please join us for dinner and for some networking. Thank you all.